presented is entitled Sensitivity and Robustness of Volterra Weiner Neural Network Estimation of Nonlinear System. The paper will be presented by Dr. Patrick Brewick from University of South California.
Hello, everyone. This contraption feels a little interesting on my face. All right, so anyway, my name is Patrick, as our chair kindly said, and I did this work with Sami Masri at the University of Southern California, along with Dr. Kasiakos from Cal State Long Beach, as well as Dr. Kosmatopoulos at the Democritus University of Thrace. So I think we can all agree that nonlinearity is reality. While it's often convenient for us in our courses and in many other places to make linearizing assumptions or to use linearization to make problems more accessible, more easily solvable, a lot of engineering is actually governed by nonlinearity. Everything from aerospace, where we have problems of aeroelasticity, to wind turbines and other flexible structures, civil structures with cable dynamics, nonlinear dynamics, even electromechanical systems with everything from nonlinear control problems all the way down to piezoelectrics and MEMS. We encounter nonlinearity in a variety of ways in engineering, and there are a variety of techniques we come up to overcoming these challenges, but I myself am a civil engineer, and in structures, the nonlinearity we often talk about is hysteresis, or hysteretic restoring forces. And so one of the most famous models that I'm sure you're all very familiar with for hysteretic restoring forces is the Blue Qin Model. And we often use this restoring force model to describe the nonlinearity in base isolation systems, or in joints and connections, or maybe in a member. And so there's a variety of nonlinearities we encounter in structures, but we often use hysteresis and hysteretic restoring forces to capture that nonlinearity. However, there's a certain memory aspect to hysteresis that makes it very difficult to deal with. So unlike regular linear restoring forces where we can use instantaneous variables and algebraic functions to capture the behavior, this memory aspect of hysteresis forces us to track it over its entirety in time and use models such as the Blue Qin and other famous variants to capture that behavior, and then also derive a bunch of various techniques to estimate this hysteretic behavior, everything from artificial neural networks to polynomial techniques to linear least squares techniques with maybe a nonlinear component using neural networks to a variety of techniques we've used. However, the accurate and efficient online identification of these nonlinear hysteretic restoring forces remains a challenge. So a lot of the techniques that we currently have work well, but maybe they rely upon batch processing, where we have to take the information as measured and then fit it to a nonlinear model. And then the model itself can be a problem, where we need to somehow find a mathematical description for nonlinearity that may not be convenient. Additionally, some of the solutions we have are not generalizable, where it works really well for a given system or component, but we can't pick it up and put it to another system or another component, another structure. And also sometimes we have this black box problem, which especially comes up with things like neural networks, where we give it input, we get output, and the output matches our measurement or whatever quantity we're trying to capture, but we actually don't know how to translate that to another system, another structure, another component. So today I'm going to talk about the Volterra Weiner neural network, which is an online, data-driven, generalizable, and most importantly, and I hope you get this from this talk, an understandable way to do online identification of nonlinear systems. And my talk today is going to talk about the sensitivity and robustness of some of the parameters in the Volterra Weiner neural network. And hopefully, after this talk, maybe I'll have a couple converts in the audience who may think about using it for their nonlinear systems and applications. So the Volterra Weiner neural network is an adaptive online estimator for nonlinear systems and operates with two parts: a linear multi-input, multi-output dynamical system that's connected to a linear in the weights neural network. And the weights of the neural network are estimated through an adaptive estimation scheme. And again, I'm a civil engineer working with structures, so the equation of motion we have here, you can see on the left. I guess I can use this. Or where we have a restoring force, external excitations, maybe ground motion, space excitation, but we're going to reorganize it in terms of acceleration, because accelerations are what we're measuring and eventually what we're trying to predict using this method. So to give you a breakdown of how this method works, we have inputs, and here our inputs are accelerations, so the measurement of the response acceleration of our structure, or also the ground accelerations or base motions if we have any of those, because again, we can measure these quantities. And then we take these inputs and put them into our multi-input, multi-output system, where we pass them through a low-pass filter that we apply in a cascading process. And then we can take that and put it inside our neural network, where we're putting it inside a vector of nonlinear activation functions, and then we're multiplying it by a series of synaptic weights. And the output of this is actually an estimate of the acceleration at the next time step. So that's what we're trying to predict. We're trying to predict the next acceleration and minimize the error in doing so. And so this is sort of the overlying hierarchy of the Volterra-Weiner neural network. However, there are two key parameters in the design of this network. The first being the weight of the nonlinear activation function. Inside those functions here, you can see it's a hyperbolic tangent sigmoidal function where this weight lambda has an influence that's strongly correlated with the input. Because obviously, if we're not careful with how we're tuned lambda, the output of this function could just be 0 if it's too small, or if lambda is very, very large, this function is always evaluated as 1. So we need to be very careful that we tune lambda to our input, especially because these nonlinear activation functions are found in both first and second order terms inside this vector of nonlinear activation functions. Additionally, the other parameter we want to be careful with is the adaptive gain, because this drives the learning rate and updates the weights of our neural network. So we need the adaptive gain to be large enough where it interfaces with the error to give us better estimates of our weights, but we need to be careful not to make it too large because that can give us an instability where we're getting into problems of overcorrecting and eventually an unstable solution. So I'm going to talk about this method using a fairly simple structure. It's just a 3-degree of freedom structure here, as you can see. Excitation is provided by a ground motion where we're simulating ground motion here using a wideband random process. And we have 3 restoring force elements in this structure, the first of which is modeled right now with a Blue Qin type nonlinearity. Now the other 2 restoring forces initially were set as linear, and that's just so we can focus our discussion right now on this first restoring force, just for simplicity terms. So this method has actually been around for a little bit of time, but the few people who have used it have never really talked about parameter selection in general. So when I first tried to use this method, one of the things I had to look at was using a parameter study just to figure out what sort of values this weight for the nonlinear activation function and the adaptive gain should take. And in doing so, I plotted these in this parameter study against the relative RMS error, where the RMS error here I'm talking about is the error in the acceleration comparing measured to predicted over the entire course of the simulation. So using this error measurement, this RMS error measurement, we can actually see that this neural network has 2 interesting sensitivities. First, with the gain, you can see there's very, very large RMS errors here between our predicted and measured responses. And that's actually due to the fact that if our gain is too large, we get that instability due to overcorrecting that drives our problem to become unstable. Additionally, there's very large error that can be due to very small values of lambda. As I mentioned earlier, if lambda is too small, our output is just 0, and so we don't get any useful information at all. So there's 2 ways we can have unstable solutions for this neural network. And as you can see, if you plot these in a planar view, you can actually find that this parameter lambda correlates very strongly with the accuracy, whereas the adaptive gain does not have nearly as strong a correlation, and that's mostly because while it does deal with accuracy somewhat, it's much more driven in terms of stability of the system. So using that parameter study, we came up with a nominal parameter set, and as you can see, for a couple different simulations here, and for each one of these simulations, we provided a different random ground motion. You can see for this first degree of freedom, and again, that's the degree of freedom that has that nonlinear restoring force element to it, you can see the difference between the measured and estimated acceleration is actually very, very close. And you can actually see here the learning rate, how steep the learning curve is, and that after only about 5 seconds or so, the RMS error converges very quickly, and we get very accurate estimates of our system. However, we wanted to do more than just 3 studies, so we actually simulated 500 times, and for each simulation, a different ground motion with similar spectral characteristics, but different time histories were input into the system. And as you can see here for this nominal parameter set, the mean of the error, the RMS error, was only about 3%. However, in 10 out of these 500 simulations, we actually got an unstable situation in which the error was driven to be too large. So clearly we had to adjust our parameter set. So we did so in 2 ways. One, turned down the gain, and the other thing we did was adjust the weight in the nonlinear activation functions. And we found that both of these led to purely stable solutions over all 500 simulations, and the error increased, but not significantly. However, it's actually much more interesting to talk about what happens when you're not training anymore. So for these types of simulations, when we have our gain turned on, we're training, we're learning, because at every step we're updating our weights, right? It's a training type process of this neural network. However, we wanted to see what would happen if we turned training off. And so when we turn training off, what we do is we use a first initial simulation, train the weights over that one simulation, and then run 500 times using those final set of weights for each subsequent simulation with different inputs, just to see how well it will perform. And as you can see, it actually performs quite well, where the error increases to only 10% for this parameter set, and it actually does even better at 7.5% for the different parameter sets. So again, we can actually do very powerful things with this neural network scheme, even when training is turned off. We do not have to keep training and adjusting our weights for every single simulation. And here's actually just a sample output you can see, again, for two different simulations, where the difference between the measured and the estimated error is actually difficult to detect. You can see some of the overestimation at certain points, but in general, the error is fairly consistent. And again, since training is turned off, there's no longer that steep learning curve. The RMS error is actually fairly constant over the course of the entire simulation. And so part of the discussion that has to happen if you're talking about weights is how do the weights converge over the course of a single simulation, because obviously if we're going to use those weights for subsequent simulations, we need to look at their behavior. And you can see that here we show the first three weights. And in our neural network, there are actually a couple hundred in total, but it's for the sake of the size of the screen and everything, we're just going to talk about the first three weights here. And you can see that while they don't purely converge, they're not asymptotically converging or asymptotically stable, we get some generally stable behavior to these weights over the course of a simulation. And then for a training off scenario, the weights at the end of this time history are what would be used for subsequent simulations. And one of the ways we need to judge how well those are going to perform is if we were to look at the final weights for every single simulation, we can see the distributions here, and we can see that they're actually fairly tightly distributed, where you can see that they all have a fairly narrow distribution even over the course of several simulations. So again, there's a certain robustness in the fact that it doesn't really matter what simulation you're training on. Generally speaking, again, generally convergent. So generally speaking, your weights are going to converge to a common distribution so you can then use them for subsequent simulations. But in addition to Blue Qin nonlinearities, we wanted to look at other types. So we looked at a polynomial type nonlinearity, and here we see a polynomial type hardening, where again we have here our restoring force element, that one nonlinear restoring force element for a couple different simulations, and you can see the hardening behavior. And we tried a couple different parameter sets for this, but what I really want to focus on now for the sake of time is just the first and last parameter set, where you can see that this parameter set here is very similar to what worked very well for the Blue Qin, but for the polynomial, it worked very, very well when training was turned on. As you can see, it's a very sharp learning curve. The error becomes very small. But as soon as we turn training off, we get much, much, much larger errors, and we have lots of error problems. And so clearly the parameter set that worked for the Blue Qin was not going to work for this type of simulation. However, we can make fairly minor adjustments, and while we sacrifice some accuracy when training is turned on, as you can see this learning curve is not as steep, all we did was adjust this weight in the nonlinear activation function. We sacrifice some accuracy, but when we turn training off, we're much more accurate now. And again, it's not perfect. This is not a perfect recreation of the acceleration, but the prediction is quite good and only about 8 to 10% error compared to the 30-35% I showed previously. So this actually works for a variety of different nonlinearity types. And the other thing we were able to do is, again, look at if we choose different parameters, look at how they perform in terms of the RMS error. And we can see here, we see the same behavior we saw with that parameter study earlier, that as you increase the weight in the nonlinear activation functions, your error improves, but that is only for training on, and you have actually a very large trade-off, because once you turn training off, you can see that even though you're quite accurate when training is on, if you turn training off, you now have much, much larger error. And so clearly you have to find somewhere in your function where you get that trade-off, and you're actually, in this region here, even though you're sacrificing some accuracy, when you turn training off, you're not losing much accuracy. And so clearly there's some problems related to overfitting and things in this neural network that you have to be keenly aware of. Finally, we applied some restoring forces, or some nonlinearity to each one of the restoring forces. So here we have the restoring force for the first element, second element, and third element, and there's a nonlinearity in each of these. And again, we tried parameter sets very much related to our initial nominal parameter set back from that original Blue Qin example, and we see they both performed pretty well. But this time, what we thought would be more informative is to see how it would perform when training is turned off if we used a less accurate solution for training. So you can see here, if you run 500 simulations, you get a distribution of the RMS error, and this is with training on every single time. But for our training off, we actually used the simulation where the error was much further away from the mean, a couple standard deviations over. But even though we used a less accurate simulation for training, we actually still had fairly robust and accurate results when training was turned off. So clearly, one of the powerful aspects of this neural network is that it is not dependent on being lucky, if you will, or being fortunate and having a highly accurate simulation for training. The way the weights behave, even if you don't have a very accurate simulation for training, when training is turned off, you can still get fairly accurate results. And this was shown to be true for both different parameter sets here. So in conclusion, we saw that the Volterra Weiner neural network is a powerful tool for online estimation of nonlinear systems and has a demonstrated sensitivity to the different parameters that I discussed, lambda and gamma. There's a proven robustness even after training is turned off. And actually, this is something I probably should have mentioned earlier, but what's also interesting about this method is it's agnostic to the topology or the type of nonlinearity. Like this, if you noticed, in this method, you don't have to actually have a specific kind of topology to your structure, and you don't have to know what type of nonlinearity you have. Whether it's Blue Qin, polynomial hardening, or some combination of the both duffing, it actually works well every time. And so it's applicable to a variety of nonlinear models. And currently, we're working on comparisons to other nonlinear identification techniques to judge just how much more powerful it is than those. So with that, I will wrap up, and thank you for your kind attention.
Thank you. Okay, any questions? Any questions?
Yeah.
How this is different from frequency response function approach, where also uses Volterra. There's a group in Sheffield, basically, which uses that approach extensively.
I'm sorry, what was the last thing you said?
Frequency response function.
Right.
You build up frequency response function. What you didn't mention about restriction, that your nonlinearity has to be small, actually, because if you don't have uniqueness in your solution, you wouldn't be able to apply that method. I
guess that's an important consideration. I mean, obviously we haven't done an exhaustive study of all different kinds of nonlinearity, but I think that's an important consideration. But I guess I've never thought about how it's different than a frequency response function in that sense.
But there is, I don't know, maybe 20 years body of work from Sheffield. Keith Warden is the name, Jeff Tomlinson, and all these groups. They have been doing that for donkey years, but the key element is there. I think it's basically assumptions are very similar, that the nonlinearity has to be small. So if you look at the linear response of the system and nonlinear response of the system, so they are saying that the nonlinear response has to be smaller than 10% basically, and then this method works.
I'm not aware of that limitation for this method, but it'd be something interesting to consider to sort of dial up the nonlinearity, if you will. Because as you saw for the final one, each degree of freedom was nonlinear to a degree, but again, I'm not quite sure how to quantify that in terms of the linear aspect of the response. But we're slowly dialing it up just to see how powerful it is, but we haven't actually come up with a quantification, if you will.
Yeah, if I may add to my co-author here, we're very familiar with the people in Sheffield, Warden, and so on working on. That's a frequency domain thing that's subject to the restriction that you mentioned. This is a time domain approach, and in fact, the more nonlinear the system is, the better it performs compared to the competition. So there is absolutely no restriction on the size of nonlinearity. If your nonlinearity is small, there are much better methods to use. But this is the point, the whole point about the Volterra neural network here, and being shown with people that have done a lot of work on robotics and control and things like this. This is extremely accurate, adaptive, and the way it's learning, as shown in here, very robust. But there is nowhere in the discussion or limitation. That's the power of neural network. All right? That it's, yeah.
You have a biased ability. If you train on one solution, you have no chance to go to the
well, okay. Of course, in any method, right, your results are only as good as what you're training, right? So if your data set, if you're outside the range, no, but any method you use, right? If the data set that you are using, this will give you the best representation. If you now have a completely different phenomenon, it's clearly, it's not.
You have a chaotic motion, you jump between the attractors. So what your system will do?
Well, as long as the data set that you provided the system is both, well, but no, but we have done some studies before. As long as you have long enough record that see, again, this is not tracking thing. This is give you the best estimate, right, in overall work. So even if you have chaotic system and so on, as long as you provide a data set for training that encompass the phenomena you're interested in, it does a good job.
Yes, I think we may have a detailed discussion after presentation.
Yeah.
Next question, please.
Patrick, thank you. We're trying to do some things similar to it for nonlinear and steady aerodynamics and trying to train the data to be able to model it. But my question to you is that, let's say some damage happens to one of the springs or one of the mass is reduced or something. Have you thought about how would you use this to do structural health monitoring or something like this?
That's actually something we're working on right now, where we have a nice data set, and we've only just begun looking into it. But I think one of the important distinctions I would make is that my hope is that you would see some change in maybe the error or something like that, but we haven't actually been able to quantify that yet, but we're currently working on a data set right now because we realize that a lot of the power in this identification is change detection, right? Whether it's health monitoring or just maybe tracking the nonlinearity itself, it's something we're working on, I guess, right now.
Okay, I have a short question for you.
Yeah, sure.
Just a short question. Is any validation data necessary to optimize the configuration of the network?
Sorry.
Is any validation data necessary to optimize the configuration of the network?
Is any like verification data? Is that what you said?
Yeah, for the traditional network, we need to use, we don't know the configuration, how to determine the number of layers and number of nodes, right? So this is a traditional network. So for your network, it's necessary to use any validation data to optimize the configuration of network.
Actually, that's one of the sort of unique things is it works differently than a traditional artificial neural network in that you really only need to give it the inputs, and then what you can do in sort of along those lines is you can decide if you want to include second order terms, third order terms, so on and so forth. And also, if I can go back really quickly, when you're designing it here in this filtering step, if you wanted to, you could, so there are other parameters besides the two I mentioned, right? So there's this filtering process where you can decide how many low-pass filters you want to apply in cascade, trying to get more information, because you could think of each low-pass filter as sort of a recursive filter, and so you could try and get more and more steps back in your time history if you really wanted to.
Okay.
And then with the weights, obviously if you're including second-order terms, you have more and more weights.
Okay.
So.
Okay. And other questions? Okay, no question. Okay. Thanks, Patrick, again. Thank you.